Okay, so notations and setup, so bear with me. This could seem a little bit tedious and boring, but we really need to have those setup and notations ready before we can talk about how we're gonna do the estimation process, okay? So just a lot of slides, just bear with me. So the confidential data, we use Y, okay, and YI. In this case, we just gonna represent the vector of response for observation I. Okay, so notice that we bold that Y because it's a vector. Okay, and we use P variables. Okay, so YI1 through YIP. So there are total P variables in the confidential data set. And keep in mind that here, direct identifiers like name or social security number is already removed. Okay, so this is de-anonymized version. Okay, so YI. Think about YI as each as the vector response of the consumer unit, each consumer unit in the consumer expenditure survey. So that will be a YI. So we use J as the variable index, okay? And you will see that J goes from 1 to P because you have P variables in total. So we know that among the P variables, some of them are synthesized, right? So we use YI, and then with the superscript S to denote. Okay, Ray just joined us. Oh yeah, so I do see. Okay, so Henrik, even if you accidentally drop off the line, I should be able to see you trying to join from my end here anyway. Okay, so we use YIS to represent the synthesized variables. And notice that we also use the bold face here just to represent it's possibly, it's possible that it's a vector. And then we use YI with superscript US. So U stands for so unsynthesized variables. So we have the synthesized variables and the unsynthesized variables. So then you're able to express your YI to be the collection of the two, okay? Because all of the variables, all of the P variables, for each variable, it's either synthesized or unsynthesized. So you're able to represent it here. And then dropping the script of I will indicate for the entire data set, okay? So imagine the entire data set is Y, is a matrix, right? And a data frame, and then you have the portion that is synthesized and you have the portion that is unsynthesized, okay? So one thing good to keep in mind, even though throughout the lecture we're gonna use for partial synthesis as the working example, but we should pay attention and notice that if you're working with fully synthetic data set, your unsynthesized set is empty set, right? So in that case, your Y just become YS, okay? But this is really just to differentiate between fully synthetic data and partially synthetic data, but without loss of generality, we're gonna use the collection of, the union, I should say, YS and YUS as the entire Y, okay? So that's the real data, okay? Everything is about the real data. And then the synthetic data, we have been using Z, okay? So you can have more than one synthetic data set. So we use Z to represent the collection of all of them. And then all of the superscript here is indicating a particular synthetic data set. So when you have more than one. So notation-wise, this is what we start with. And okay, so we have notations now for the original data and for the synthetic data. And then we have to, as we know, similar, so if you recall in the identification disclosure risk situation, we also make assumptions about what the intruder knows and doesn't know, right? So for the attribute disclosure, we also have to make assumptions, and we're trying to express assumptions mathematically. And so the first thing we know that what the intruder is trying to learn is the true value of YIS for some record I in Y. Okay, so remember YIS is the synthesized variable, the vector of it. It could be univariate, it could be multivariate, depends. For the CE example we're gonna do is univariate, but we use a vector to represent it regardless. So we're trying to, the intruder is trying to learn the value of this for some record in Y, okay? So that's the goal, that's what the intruder is trying to do. And what is available to the intruder? We're breaking the information down into 3 pieces because each of this is going to come into play later when we're trying to estimate that probability, the probability of attribute disclosure. So the first one is, well, imagine once people have Z, which is the released synthetic data, and if the intruder knows that some variables are never synthesized, that means they will have all of the unsynthesized values of, all of the values of the unsynthesized variables for all of the observations, right? So for example, in the CE data, we know that you have synthesized the income, okay? And you have unsynthesized. I think you have race, what is it, expenditure, and urban rural status. Okay. So notice that we're not talking about which variables to use to do the synthesis yet. Okay, that is something altogether else. Okay, we're just talking about what's available to the intruder once we release Z, which is the released synthetic data set. So if the intruder actually knows that all of this are never synthesized, that means whatever appears in Z is whatever in Y itself. I should say in YUS. So US, we know, is the unsynthesized portion of the data set. So all of this will be available to the intruder, and that's for all of the observations. Okay, so anything unsynthesized, because it's partial synthesis we're looking at right now, it's released in Z, so it's available to the intruder. And we also have two other pieces of information that we assume that the intruder will know, which we're gonna like break them into two parts so we can talk about them separately. We use A to represent any auxiliary information known by the intruder about records in Y, okay? So we say it, A stands for auxiliary information here. And it is information known by the intruder about records in Y, right? So it's in the original data. So we know that, so YUS is actually part of Y, right? Because we know that Y is YUS and then YS based on the notation that we had earlier. Or my Y looks like a 5, so you know what I mean here, okay? And so this is A, what we're talking about is in addition to the YUS, we're trying to make assumption what the intruder would know about anything else about the records in the YS. Okay, so keep in mind that generically we say that it's about Y, but it's really, once they know the YUS, it's really about any information, any extra information they might know about the YS here, okay? And then the last piece is S. We define it as any information known by the intruder about the process of generating Z, okay? So this, as you probably have guessed and also remembered, a lot of times for publicly available synthetic data that the agency releases, for example, like the synthetic LBD, remember? We're looking at the longitudinal business database. Remember that paper that we read, this application? So that, if you remember, is actually a paper, describing in detail what they do. Well, you might argue that it's not in detail because some of them we still didn't understand how they actually did it for the synthesis model, but you can imagine that for publicly available synthetic data like the SYNLBD that the Census Bureau published, for example, that there's always, in a lot of cases, like accompanying either manuscript or even, I should say, like technical report that the researcher is going to publish along the way, which will include very detailed information about the synthesis model, or even about how they choose prior, et cetera, et cetera. So it is sensible to make assumption about, say, S, what we're doing here, any information known by the intruder about the process of generating the synthetic data, okay? So we are breaking all of the information available to the intruder into the 3 categories here, and then we're gonna keep them as we go along the way to do our estimation process. All right, so hopefully these are clear enough. And so lastly, over here, we need to define a few more things. And so the first one is we use capital YIS to represent the random variable representing the intruder's uncertain knowledge about YIS. So the smaller y and capital Y. And essentially, what the intruder is looking for is the distribution equation 1, right? So look at what equation 1 is doing. is YIS given Z, YUS, and AS. Okay, and we also express equation 2, which when we have yi star here is a particular guess, possible guess of YIS. So 1 and 2 will be equivalent in this case. Right? I wrote down like the 2 bullet points down here to think about, well, in what situation, for example, what if YIS is a vector of categorical variables? What if YIS is a vector of continuous variables? How can we think about these 2 distributions in those contexts? So I'm gonna actually let you talk to your, well, I'm gonna do the breakout rooms in a second. Give you the time to talk to your breakout room group people, peers in that group, just to have a sense of what you think, what we should be doing moving forward. Okay, and sorry, this should be a small y, I think. Yeah, so this one should be a small y. Can I like that? Be a small ys, because we use capital letter to represent anything random, and the small letter to represent anything known. Okay, so yeah, so let me actually. Okay, we wrote down here when y is a vector of categorical variables or when y is a vector of continuous variables, what you can do. And to some degree, it could be very similar to what we were thinking back then about the identification risk, right? Like whether it's exact the same as the categorical cases or within a certain distance from the continuous cases. So here, the goal is that we're trying to find or seek the distribution of this PY, YIS, which is the random guess, equals to a particular guess, Y star, given what we know from the release data, given what we know about the unsynthesized variables or the data, and then any other information that is contained in A and S. Okay, so this is the basic setup of what we're trying to do. And if you have done the reading, you will notice that soonish from here, we're gonna break, not break, but like factor, use Bayes' rule to factor this equation 2 into different pieces. And then some piece will be in a way about likelihood, and some piece in a way will be about prior, okay? So if you think about this equation 2, what we're doing is essentially, well, you can think of this as a quantity of the, it's a posterior that we're trying to find, as you will see soon in our setup. But here, it's at this point on this page, it's important to think about the different nature, right? You can have categorical responses or like variables in your YIS. You could also have a continuous variable or a vector of them. And you could have combinations. Okay, Maggie's is joining us as well. Welcome. You can have combinations of different types of variables in the same YIS. Okay, so it's important to think about like the differences and similarities, and then maybe just in your head have a working example going forward. Okay, and for our working example in the lecture is about the CE data. So the YIS that we're going to do later actually is a scalar. Okay, it's not a vector. It's just going to be the guess of the synthesized income for each CUI, and then that is continuous. Okay, so that's the working example that we have. But maybe keep in mind what you're trying to do for your project as we go through this, because after this, I'm pretty sure you will have to dig into a little bit more to see what it means in your specific example. Questions, comments?
How do we know how much information an intruder has?
Yeah, good point. So we have to make a lot of strong opinions or strong strong assumptions here. So Ted's question, I guess, is directly coming back to this slide, is about why US, A, and S, all of this information, how do we know for sure? Okay, so like I said, it's sort of open-ended. We have to make certain assumptions, especially later you're going to see that we have to make some very strong assumptions about certain certain information available to the intruder, because otherwise the the computation going to be too much to do. Okay, so keep that in mind that this is open-ended, and we're going to make some very strong assumption soon. One thing is to make the computation feasible. You'll see soon why that is the case. But also you can argue that when you make super strong assumption, if your risks are low under those circumstances, in those scenarios, when you have very strong assumptions about what the intruder knows, when we say strong, it's just like the intruder knows pretty much everything. Okay, and if the risks will be acceptable in that kind of situation, then when you have some weaker assumption, assuming that the intruder probably doesn't know as much as we thought they will be knowing, and then in those weaker assumption situation, the risk will still be acceptable. Okay, so we're sort of thinking about the worst case scenario going forward, but Ted's question is totally valid. Like, how do we know exactly what the intruder will know? And this is, again, very similar to what we're dealing with the identification risk as well. We have to make certain assumptions. Yeah, Isaac, go ahead.
And I was just wondering from the reading that within a certain distance piece, is it the same logic for that? Like distance is kind of a reasonable parameter set by the user, or is there like a standard, like do you use like a z-score? Or,
yeah,
is there something?
Yeah, so you're talking about the underlined part here, right? Within certain distance?
Yeah.
Yeah, right. So I wrote it there in the slides, mostly because I think there's certain analogy to the thing that we've been thinking about with the identification risk when we think about the continuous last time, right? So the thing is, so imagine, like, just look at equation 2 for a second. This is actually a good point to pause. Just look at equation 2. So when YIS, let's just say one categorical variable. Let's think about univariate in this case. If it's a categorical variable, then, and let's just say it has 5 levels. Let's just say maybe 6, like marital status has 6 value levels, right? So your Y star for that YIS could just be one of the 6, right? Because I'm just exhausting all of the possible outcomes for that variable. So what we mean is that we are trying to compute equation 2 for all of the different 6 possible values of Y star, and then look at which one is most likely or least likely. And then one of them going to be the truth, right? So we can compare the true value, the probability of guessing the true value, comparing that to the probability of guessing the non-true values and see how high that is, right? But now if equation 2, let's just say we're looking at univariate continuous variable, just like the income. If you're doing like strictly equaling like Y star, right? And then that will be very similar to the issue that we had before, right? When we're doing identification disclosure, well, exact matching for continuous variable almost likely going to get 0 because it's a continuous variable, right? So that's another thing why we write it as a within certain distance. But I should say that in the demo that I would do, I also just, I mean, you have to do a lot of simplification when you actually do the calculation, but the general idea here is that we're trying to think about, yeah, if you think about the certain distance idea, like the identification risk, then it's also like a radius that maybe you have to assume the intruder was thinking, right? Or like whoever else is thinking. So in short, there are a lot of assumptions being made here, and which will be why people do not like those kind of approaches, right? Like it's too much you have to assume, and how am I supposed to know which assumption is the right one to make? Okay, so I mean, those are fair comments. I think it's totally good to make those and good to keep those in mind. But regardless, this framework that we're presenting now, I think, is still pretty neat as a way to figure out, well, even though this is really challenging, there are certain ways that we can make this work, okay? Even though, as a compromise, we have to do a lot of assumptions, okay? But along the way, you're gonna see a lot of, I think, like I said at the beginning, like some computing techniques that I think will be really neat overall. And in fact, as I was preparing this, I had to go back to my notes, like in grad school, like 5 years ago, looking at this. It's actually in a drive, not in my computer anymore, and then I have to go into and then looking at that. It's good, refreshing even my memory and trying to figure out how things were done, at least back then when I was doing it for the first time. Okay, so there are a lot of things involved. So I think, I mean, overall, this is pretty, like, even more related to like real research than just looking at like a set of rules and then how things can be done. But now many things are open-ended, and I think that will be, hopefully you will find it more, more interesting than just like doing homework problems and stuff. All right, so, okay, so moving forward, what we're gonna do is we, as the confidential data holder, because we are the people doing the synthesis and trying to release them, so we have to evaluate the risks, right? So we're gonna have to make assumptions on the level of intruder's knowledge. So this is related to what was asked earlier, and then how to approximate the actual probability or like the distribution here that we're trying to compute. Okay, so I was already hinting on we're gonna use some Bayesian thinking, and you will see that we're gonna break it using Bayes rule and then doing it step by step.